Hello everyone. The next video I consider for you in the playlist Solid Mechanics is about a parameter that depends on the material. It's called the bulk modulus, which you typically define it for hydrostatic pressure, and there is another thing that is related to the volumetric strain. So let's talk about this parameter. So the bulk modulus K is a measurement of material resistance to uniform compression. So if you squeeze some material from all different directions with the same amount, with same pressure, how much could you reduce the volume of the material? How much you could compress the material? And so it is defined as the hydrostatic stress over volumetric strain. And first, we have to see what is hydrostatic pressure means, or stress. So if you put material under water, why do you call it hydrostatic? So if this is water, right, this is a tank of water, and you put some material underwater, right? What kind of pressure do you expect this material to experience underwater? So this is a small cube that you put underwater. And if it's a small dimension, then from all these different directions, the only thing it will be exposed to, or it will be applied to the part, is the pressure in that location. And again, if these dimensions are very, very small, if it's like an infinitesimal element, all these pressures are the same because they depend on the depth of the water, and they are equal. And since there is no other force, and the water does not move here, there is no motion in the water, assume that the water is static water, right? And this does not move. We call this hydro, means water. Static pressure means the pressure coming from the water that is not moving, and they're all P, right? This picture. So we can say that all normal stresses are sigma x, sigma y, sigma z. They are all equal to negative P, and there is no shear. All the shears are zero, whether xy or xz or yz. They are all zero in this case. And so what's the effect of that? The only effect they have is to squeeze this element, and the pressure is the goal. The goal is to squeeze this, right, and break it and make it implode, basically. And you can see that in different examples, like when you design the submarines, correct? You know that the pressure of the water is the only one that makes this submarine collapse. So, and goes basically does the implosion, or goes basically collapses inside. Now, implosion is not the exact correct word for collapsing inside, but this is what you have. Now, so hydrostatic stress, the value of it is negative P. And the other thing we need to define is called volumetric strain. Remember, strain was defined as change in the length over length. Now, if you define it for volume, then it's going to be change in the volume over initial volume. That is called what? Volumetric strain. Okay? Yep. So the bulk modulus is negative P over delta V over V. Now, what kind of entity is that? Clearly, this guy has no units. It's volume over volume. So the unit of K, you see, is the same as unit of pressure, so it is going to be Pascal or PSI, clearly. The unit of bulk modulus is the same as unit of stress, or Young modulus, or G. Now, what does this K have to do with E and G? Is this related to those other constants of the material? The answer is yes, it is. How do we find that? Well, here we need to find the strain components of this element that is under hydrostatic pressure. Now, since all of the sigmas are the same, clearly all of the epsilons are going to be the same. And how much are they? Remember the Hooke's law that says epsilon xx was what? If you remember, it was 1 over E of sigma xx minus nu times sigma yy minus nu times sigma zz, correct? So if I replace all of these sigmas with negative P, this is the epsilon that you will find. And if you factor it out and clean it up, this is the number that you will get. Okay? Now, one thing that is important to pay attention to is the sign of this K is positive. Why? Because delta V over V is negative. Initial V is positive, but when you squeeze the material, delta V is negative. The material will shrink, the volume will go down, and since there is another negative behind this formula here, guess what's going to happen? The whole thing will be positive, okay? So you are dividing a negative by another negative, you are going to get a positive number. Another way to look at it is through this formula here. If you look here, or let's look at it from the final formula. So let's first derive the final formula, and then we look at it and we'll see that why this K should be always positive. So let's hold on for a second. Let me derive the K, and then we're going to look at it again. So these are the normal strains in all directions, right? They are all equal. Good. Now the volumetric strain, delta V, is equal to epsilon x plus y plus z. And since each one of them is negative P over E 1 minus 2 nu, it's going to be negative 3P over E times 1 minus 2 nu. The first question is, where does this come from? How did you get this one? Well, that's not super hard to show. Why? Because if I say, what is the new V, V new, or V final? What is the final volume after you applied all of these strains? How much is that? Well, it is equal to the new dimension, right? And let's say initially we started with all equal dimensions, whatever dimension that you want. So let's say they were all A. Okay, in the beginning they were all A. So the initial volume, this V, was A cubed. Now, how much is the new volume after all the strains are applied? Well, if the strain in the x direction is epsilon x, this is equal to the change in the length in the x direction over the initial length in the x direction. Now, the initial length in all directions was A, so clearly you see that delta Lx is equal to A times epsilon x. Correct? That is change in the length. So what is the final length? The final length is the initial length plus the change in the length. Now, of course, everything is x here. And this guy was A, and this guy is A epsilon x. So you're going to get A times 1 plus epsilon x. So if you look at your volume, it's going to be A times 1 plus epsilon x, that is the new dimension in the x direction, times A times 1 plus epsilon y times A times 1 plus epsilon z. Okay? Now, consider in this case, all of these epsilons are the same, right? All of these epsilons are all the same. Let's just call it epsilon. All of these 3 epsilons are the same. So if you look at it, it's basically going to be A cubed times 1 plus epsilon to the power 3. Correct? This is the final volume. So what is delta V? Delta V is going to be A cubed times 1 plus epsilon cubed, and then minus initial volume, which is A cubed. And if you divide it by V, right, because that is what we need to get for the volumetric strain, this is going to be, and this V is initial V, so it is going to be divided by A cubed. And if you simplify this, correct, this is, you can expand this, this is going to be 1 plus 3 epsilon squared plus 3 epsilon plus epsilon cubed. And this one term of it would cancel out, and you will get this. And if you divide by A, the A's would cancel out, correct? So you will basically get this one. Now, in these 3, this epsilon, remember, is a small number. So when you raise it to the power 2 and power 3, they are much smaller than the epsilon itself. So for instance, let's say epsilon is 0.001, okay? Now, if that's the case, then 3 epsilon is going to be 0.003, right? I just want to show you. And then 3 epsilon squared is going to be this. And epsilon cubed is going to have even more, correct? So you're going to get 9. So 4, 5, 6, 7, 8, 9, and there is a 1 here. So you see these two are much smaller than this, and you can ignore these higher order terms compared to the linear terms. So the only term you really have is 3 epsilon, or if you write it in terms of the original one, it is epsilon x plus epsilon y plus epsilon z, if you expand it based on the original ones. And that is exactly what you can see here. Now, since they are all equal and we just found them, we're going to plug it in. So this is the volumetric strain. And we just replace it up down here. In the formula, this P and that P would cancel out. This negative and that negative would cancel out. And you're going to get E over 3 times 1 minus 2 nu. So the formula we have for bulk modulus, as you can see, it depends on the Young modulus and the Poisson's ratio. Okay, so if you want a formula for bulk modulus, there we go. We found it. E over 3 times 1 minus 2 nu. Again, assuming that the material is isotropic and it has the same E and nu in all directions. Good. Now, from here, you can also see that K is a positive number. Not only you can see it from the original definition, you can see it from here. You might say, how come? Well, E is always positive. But remember the nu, if you remember nu, it had a range. It was between 0 and 1/2, if you remember that. Okay, and from here, you can see that then 1 minus 2 nu is clearly positive, and so the whole K is positive. Now, this is actually the other way around. So, if I want to be honest with you, because K is positive, it has to be positive. If K is not positive, it means when you squeeze the material, it will increase its volume rather than shrinking its volume. Okay, so because this delta V is negative and this guy is negative and V is positive, K has to be positive. Okay, now if I come back and in this bottom one say, hey, this whole K is positive. This whole thing is positive. And I know the numerator of it is positive, so the denominator, which is 3 times 1 minus 2 nu, this guy has to be positive. And guess what? 3 has no effect, so 1 minus 2 nu is positive. That means nu should be less than 1/2. So if somebody says, where did you get the fact that the Poisson's ratio is less than 1/2, and of course it should be bigger than 0, where did you get this one from? You say from the fact that the bulk modulus is equal to this and the bulk modulus is positive, right? If I go back and show you when we talked about the basics of solid mechanics, right? I guess it's here. When we introduce nu, let's go and find the nu here. This is where it is. We said that the nu is between 0 and 0.5. Where do we get that? Right? That's exactly where we got it. Right here. The definition of the bulk modulus. Okay, so this is bulk modulus. This is why nu is between 0 and 1/2. And that's the definition of bulk modulus. And of course, the definition of hydrostatic pressure and the definition of volumetric strain. So we learn a bunch of new definitions. But now we get to the question that I always like the most in any lecture. Where would you use this bulk modulus, correct? I introduced the formula for it, all sorts of things. Where is the application of this bulk modulus? Well, let's take a look at some applications. One is clearly in material design, in engineering. especially if you are dealing with the parts that are underwater, like submarines or some parts of the pressure vessels that is inside the water. Or it could be in aerospace. If you look at an airplane in the air, and almost on any element in the air, that's like submerging it in water and you submerge it in air. So they are also subjected to the air pressure as opposed to water pressure. So clearly, for anything that is inside any fluid and is exposed to hydrostatic pressure, you have to look at the bulk modulus of that when you want to design the part, because if you know the pressure and if you know the volume of the part, when you know K, that means you can estimate how much the volume of the part is going to change, and is that acceptable or not? Is that within the linear limits? Is that within below the linear or proportional limits or not? So that is very important anytime an object is submerged into fluid. The other thing is about the fluid itself. So we want to know whether the fluid is compressible or not compressible. We can look at the bulk modulus values. Well, if you look here, this delta V is actually in the denominator. If you simplify this is negative PV over delta V. So if you can squeeze a material and you can change the volume of it significantly, that means this delta V is a big number. That means K has to be small. So compressible material, they have small K's. On the other hand, if you cannot easily compress them and change their volume, means their delta V is small, then K has to be a big number. So looking at K can tell you whether material is compressible or not. And you can look at some common material here in this table. You look at the air and look at how small the K of air is, which means you can squeeze air to very, very small volumes and high pressures. So because it's very small, it's highly compressible. If you look at water, it's not really a small number. It's way bigger than 1, 2.2, and that means almost water is not compressible. Mercury is way, way higher, so it's incompressible. But if you look at rubber, it's a small number, so rubber is highly compressible. Polystyrene, you see, it's still compressible. It's less than 1. Glass, huge. Steel, very, very big. Diamond, the biggest one. Diamond, you can barely do anything to it, so it's extremely incompressible, very, very hard. Okay, so small case, very compressible. Large case, not compressible. That is another application of knowing what kind of material you're dealing with. The other application is acoustics. In acoustics, maybe I'll do a video on this. If you want to calculate the speed of sound propagation in solids, liquids, or gases, then the formula for it, based on the K, based on the bulk modulus, is for solids, it's this formula, K plus 4 over 3G under square root over rho. For liquids, because liquids cannot have shear modulus, for liquids, you cannot apply shear to the liquids. So for liquids, G is equal to 0. So that term goes to 0, you get the square root K over rho. This is the speed of sound propagation in a liquid like water. So if you use sonar waves underwater, the speed of sound propagation depends on the bulk modulus of water, which is basically this number divided by the density of the water. And for solid, it's this number. And for ideal gas, not as regular gas, for ideal gas, it's this formula here, where E is there, rho is there, and the Poisson's ratio is there. And of course, if you have any structure in deep sea or high altitude, you want to look at that. Now, actually, when you look at it, this number 4 is very similar to number 1. So 4 and 1 are the same, basically. So I can get rid of 4, really. And so anytime you're dealing with structures in deep water or in high air altitude, or any altitude in air, you want to look at the bulk modulus when you're selecting the material, or you want to analyze the change in the volume. So these are some applications of the bulk modulus. Hopefully this video was useful to you. I'll see you in the next lecture. Thank you.